their oscillation up and down is not responsible for the momentum in the direction of wave. So the momentum is carried, impulse is a transfer in the direction of energy, but that is not coming because of the mv. In wave chapter also, particles are oscillating up and down, and energy carried in the perpendicular directions. Impulse, this impulse is in the direction of your energy propagation. So in this wave chapter also, you can think that this mass was not responsible for the momentum transfer. Okay. So here I can say that as my energy is propagating, okay, as energy is going to propagating, so this energy propagations not only develop the pressures, along with the pressures, it is developing here the momentum transfer also is there, impulse transfer is there, right? Impulse transfer here means momentum transfer, same thing. The momentum is going to be transfers. So how much is the momentum transfer? Momentum transfer. So momentum transfer, I can call it here as a P. That is simply energy by C. Energy transferred by C. Or if I write here that momentum transfer per second. Momentum transfer per second, if I'm going to say here, rate of momentum transfer. Okay, momentum transfer here per seconds. So this is nothing but this is equal to my energy transferred per second divided by C. So what is my this term energy transferred per second? It's the nothing but power, right? So it is a power only. So here is a power. Power transfer divided by C. Now we have a lot of P here. So I'm not using the P symbols. Okay, momentum also P, pressure also P, and power also P. So I'm just writing here the name. Okay? Momentum transfer per seconds. I'm changing here the different symbol here as a K. So what is my momentum transfer? Momentum transfer is nothing but a power transfer. So that's one more interesting relation I'm getting here is
was Sir, you are muted, sir.
Achha, that's why you're laughing. Okay. So can you hear me now?
Sir, host is our friend, sir, not Narayana College.
Repeat again. What?
Host is our friend, sir, Satvik.
Oh. So actually it was initially I was a host, na? So it get suddenly disconnected, so it has shifted the host to someone else. It's no problem.
Yes, sir.
So what I'm saying here in this situation here, is try to understand here from our relation based. So idea is that impulse is there in the radiations. Not only radiation has a powers, this power can do the work, and the work can develop here the pressures, and pressure can develop here the force, and force can transfer here the impulse. So that is the important thing is that, so there is a momentum transfer. Now, understand here one thing, this momentum transfer, I have taken the symbol K. That momentum transfer is not a force. I'm not saying it is a force. Okay, momentum transferred per second is not a force. So this you have to be slightly understand here. What is the difference between that momentum transferred per second and the force? So according to mechanics point of view, if we go by mechanics point of view, so mechanics says that when momentum change per second, that is the force. So here it is not a change of momentum happening. It is a transfer of momentum happening. Meaning thereby, suppose there is a radiations and the radiation go like a waters, flow like a waters. So as there is going to be a momentum is going to be crossed. So in 1 second over this cross section, how much momentum transferred, that is power by C. So as power is crossing, okay, as my power is going to be crossings, so momentum is going to be crossings. So here it is a momentum transfer over the cross sections, right? So it is not a force. Okay, that's not a force. So momentum transferred per second is directly linked with my power transfer per second. Okay, understand the point here? How momentum transfer is equals to my impulse. Impulse here is basically impulse in the situations. Impulse is a momentums. Impulse means change in the momentum. You can say that if something is going to be bigger from the rest and it is gaining here the motions, so get here the impulse, and that is equal to the momentum here. Right. Sorry, okay. So I hope you understand this. This is a very important idea is this. Impulse transfers and momentum transfers. So how is that? Power by C. But you can also relate power is nothing but intensity dot A. So you can remember this way also. I dot A by C. So you can also remember in terms of intensity. So I dot C, yesterday we had discussed it's a pressures. Okay, that term we discussed the pressures. So I can relate these two. So momentum transfer is nothing but the pressure dot area. So it is not a pressure into area, right? It is not a pressure into area. It is a pressure dot area. Okay, so we can say in this case, it is going to be here my IA cos theta divided by C. So we can think of momentum transfer is equals to a pressures PA cos theta. So intensity is a scalar quantity, it is not a vector quantity. And pressure is also is a scalar quantity, it is not a vector quantity. So here I'm writing it as a vectors just to indicate that only cross-section area is responsible. Okay, so area in the directions of my intensity, that only responsible for the momentums. Okay, so you can think of this way also. If you have a problem with the dot product, you can think of transfer as a I A parallel with the C. So what do you mean by A parallels? Cross-section area. So my momentum transfer, this is an easy way to remember here, is momentum transfer is the power by C. And power is nothing but intensity into our cross-section area. So momentum transfer is intensity multiply with the cross-section area by C. Same way here also, you can also write in this way. You can relate with the momentum transfer, you can relate with the pressure also. Pressure into cross-section area. So I don't suggest you to remember many formulas. It is better to remember only this one formula here. Okay, so it is enough. So what is my K here? K is the power by C. So it's play a very important role here. Okay, because it is a flow momentums. It is going to be a flow, a momentum in the flow. Just like a water flow has a momentums, same way, exactly same way, you're going to be have a momentum in the flow, right? So it's an interesting concept here is. So related to this interesting concept, there is going to be questions are there, many questions are there. So few questions we can understand here, we can relate what type of IIT is going to be asked you the question here. What IIT can ask you? So a simple question IIT can ask you, right? Very basic question they can ask you here. So first they can ask you here, let's say this is going to be my plate is theirs. You can imagine here a plate. This plate can be circular or any plate, doesn't matter. Shape is not matter here. So any shape you can consider for the plate. Let's say this is a plate. And the light is falling on this plate. Okay. So my light is going to falling here with the intensity here I. Intensity is I. And it is going to fall on the plate. So I can ask you here, how much force is experienced by the plate? Okay. How much force is experienced by the plate because of radiations? How much force experienced by the plate due to radiations, radiation force? How much force experienced by the plate due to radiations? Two cases you can consider here. If reflection is not there, or second, reflection is 100%. Zero reflections, okay? No reflections. And second case is 100% reflections. Third, you can also add here, if my reflection is neither 0 nor 1, in general, any R value is there. So how much is the force experienced by the plate, right? So this plate area is given here as the A. Area of the plate here is A. Now in this situations, you can go through, you can do this with a two-way. The first method is from the pressure, you can find out the force. And second method is from the impulse transfer, you can also find out the force. So both of the way you can find out the force. Two ways are there to find out the force. Two methods are there to find out the force.
Sir, it's IA by C, sir, for first case.
IA by C. First case is IA by C, correct?
Second case 2A is 2A by C, sir.
Yes, correct. So to solve this type of situation here, reflection effects, how we deal with the reflection effects, very simple idea I told you to deal with the reflection effect is, you imagine incident wave separately and reflected wave separately. Because in our mathematics, we have no idea to turn the incident into a reflections. So all this mathematics we had to write, we assume that incident ray is coming, I just keep on going. Okay, in the wave chapter also we have discussed that it will keep on going up to the infinity. And you can imagine that reflected ray is coming from the infinity. So incident wave and the reflected waves are going to be theirs together. So we have incident intensity and we have reflected intensity. If I say incident intensity is I, so what is my reflected intensity? R times I. R times the intensity here falls. If I go for my this situations from momentum transfers, so as just like a ball, you can feel like a ball. Even though it is not a ball, but you can just feel like a ball. So I'm going to be have a momentum hitting on the plate, and it is going to be get transferred. So then this reflected one is also going to be transferring here the momentums. Now you can notice that initial momentum is downward and final momentum is upward. And here momentum is a vector quantity. So momentum change. So my incident wave is transferring the downward and my reflected wave transfer the momentum in the upward direction. So who changed the momentum of the light? Who changed? Oh yes, R is always between 0 and 1. You're right. R means how much part of the energy reflected. Yesterday I told you that reflection coefficient means the energy reflected divided by energy incident. Okay. So what I'm saying is that here is the momentum is going to be changed. And who changed the momentums? That is changed by our plate. So I can say that the force on the plate is nothing but the force on radiations. And how much is the force given on the radiation? I can say this momentum change. So you have changed its momentums. Okay? So you can think of K is a vector quantity because it's momentums. It's carry here the directions. Now direction is important. Pressure is a scalar quantity, but K is a vector quantity. Momentum, impulse, they are vector quantity. So it is carrying the impulse in the downward direction. Okay? And what is my K? So K here is my power by C. So I can say here the powers. What is the initial power here is? So it's going to be here my final powers, power reflected powers. Okay. P is going to confuse. So I can write here, this is going to be I dot A by C. It is better to remember this way. So K here is P confused with the pressure. So power we can write here as I dot A. So what is my K finals? K final, I can say here my incident intensity dot A divided by C minus reflected dot A divided by C. If I consider my upward direction as a positive, then your downward direction is going to be negative. Okay. So one negative sign is going to be coming because of reverse sign. So I can say here this is nothing but Kf plus Ki. So as a magnitude, they are going to be add up. Direction wise, they are opposite. So as a magnitude, they are going to be add up. What is the angle here between my area? Which area I have to consider here? It's a cross section area. So cross section area is always parallel area to my incident rays, to my intensities. So this is crossing, and this is my area of cross section here is also A. Simply, I can say here this is going to be IA by C. Then my reflected rays are crossing through the same area. Reflected rays are crossing through the same area, so it is going to be RIA by C, angle 0, 0. So what is the force on the plate I'm getting is? Force on the plate, we are getting here, it's I by C, 1 plus R into A. That is the force on the plate. So that force, this force, why this force is going to be exerted here? This force is going to be exerted because this plate is responsible for the change in the direction of momentum transfer. Okay. So if the radiation has a momentums and you changing the direction of the radiation momentums, so action has equal and opposite reactions. That's our Newton's law here. So you are changing the momentum of the one body, it will change the momentum of second body also. Okay, so momentum is conserved in the universe. So if one body lose the momentum, second body here gain the momentums. So radiations are changing, or if the radiation is losing its momentum, so plate will gain the momentums. Right? So I hope you understand here the force on the plate. So force on the plate, you can also see with I by C is the pressure, instant pressures. Ri by C, that was my pressure of the reflected rays. So from the pressure also you can come to the same conclusion here. The pressure into area plus here's pressure into area. So you can say that both incident and reflected rays, they add up their pressures. Okay. So this will be nothing but total pressures, pressure into area. So we can get the same result from the pressure into area also. Okay, that's the net pressure is theirs, I by C. So I can get the force from the pressure terms also. So two way you can come to the force. Why delta K is equal to force? I told you that K is what? It is the momentum. Change of momentum is a force. And here K is not a total momentum, it is a per second momentum. K is a per second momentum. So change of K is a momentum change per second. And momentum change per second is going to be a force. You can also think this way, K is an impulse. So it is a per second impulse. Okay, I've taken here as a per second impulse. So per second impulse, if impulse changes here per second, that's nothing but a force. So anyone else has a doubt here? Because of the shortage of the symbol, I have used here K. We don't have any specific symbol for this momentum transfers. The most logical symbol should be P only, but P is using so many confusion. The pressure, power, momentum also P. So I'm using here the symbol K. So right, I hope you understand how to find out the force here. Easy. Very good. So I can twist the situation slightly here. So simple twist is theirs, and the simple twist is that light come at an angle, slight angles. So instant angle is theirs. Then what is the force on the plate? Same thing, everything is same. So we have a plate. Plate is going to be have a same area is theirs. And now the radiations are going to be falling on the plate at certain angles. It is come from the side. It is coming here from the side. So is that go 100% reflections? We don't know. Part of the energy is going to be reflected and part is going to be absorbed. So let's say my radiations are going to be coming here. It's going to be coming over here. So I is the instant energy. So now what is the force? Find the force on the plate. Find the force on the plate if we have a reflections coefficient R. Reflection coefficient is R. Okay, we can approach in the same way as our last question here. So how are you going to do that? So I'm going to be divided into two parts, instant wave and reflected waves. So my effect of the instant wave, we can separate out from the effect of the reflected wave. So both effects are going to be separate terms. The instant wave is now coming from this inclined situations. It is coming in the inclined way. Okay. And we assume that this incident ray is going to be continue. It is just passing. It is passing through the plate. And same way, my reflected light is also going to be coming from the infinity and it is passing through the plate. Reflected light is this, okay? And from where the reflected light is coming? Reflected light is not coming from the upper side. It is instant light. Reflected light is not coming from the upside. Reflected light is coming from the downside. Okay, so this way you need to be assumed, right? So two cases you need to be considered here. Now I can think of that there is a momentum is carried by the light in this direction, and now final momentum is carried in this direction. So momentum has been changed the directions. So if my momentum has been changed, so who is responsible for the change? Plate is responsible for the change. So simply we can say here this k vectors. Simply I can say here my k vector, change in the k vector is responsible for my forces. Simply I'm going to have a k vector is there. So we have some k initials. I'm going to have some k finals. Or as a concept here, I can say this change. The change of the k is nothing but it's a force, radiation force. Now the angle they are making with this normal angle here is theta. Incident angle is my theta. Reflected angle is also going to be a theta, right? So what is that my cos component cancel out? It's not sure because k final and k initials, they are not same value. So what is my k final and k initials? K is our power by C. Power is I dot A. Okay. Intensity into my cross section area. So in this case, if you consider my intensity and the area, so they are going to be have an angle. So this angle is our theta. Area is there downward. Intensity is going to be here this way. So what is the angle between the intensity and the area? Intensity and the area. This angle is going to be my A. Theta only, no? Yes, theta only. So incident angle is going to become my area and the I angles. Same way, this side, you're going to be go intensity is going to be transferred this way. Area is going to be somewhat in my up direction. So you're crossing with the same angle here, theta. So K as a formula, you can write it here as IA cos theta by C. Okay, mostly your IA cos theta is used here. Right? So any change happens, the magnitude of my K is IA cos theta by C, or more better here is a power by C. Momentum transfer is a power by C. So there is a power in the radiation. That's why there's a momentum in the radiations. But it's a momentum is a vector quantity. Even though power is a scalar quantity, momentum is a vector quantity. And the direction of flow, you have a momentums. So if you are changing the momentum of the radiations, you need a force. Take it up. Okay. So if you are changing here this k vectors, so now it's a vector additions. So try that and tell me what is the net force coming. In which direction the force is coming. So here's a one mistake generally happens in the books. One mistake is generally they do in the book is, if you are thinking from the pressure point of view only, if you're just thinking from the pressure point of view only, then you are generally take the force into a perpendicular directions. You forget about the parallel component of the force. So in most of the books, that's the mistake is theirs. They only take up parallel component of the force. They don't consider this. So they only consider perpendicular component. They don't consider the parallel components. If the radiations are coming from the interline, there is a force in the parallel direction also, not only perpendiculars. Okay, so that is a little mistake is there in many books, not only in one books. In many books, you can find out. So answer is given only because of pressures. Pressure is one part of the force. Pressure is not the total force here. There's two different phenomena responsible for the force. Understand? There is two different phenomena responsible here for the force, even though they are linked together. Even though they are linked together. One is the momentum transfer perpendicular to the plate. So momentum transfer perpendicular to the plate that generate pressures. But momentum is also transferred along the plate. So momentum transfer along the plate that does not give pressures. Okay. So this force has a two part, one because of pressure and one because of without pressures. Through the pressure concept alone, you can't get the total force. So that little mistake happens and is common in every book. So be careful when you are doing the problems, yes. Okay, what happened? So what is the common problem here? I hope you understand this point here. Hello, can you hear me? You can hear me. So got any answer? So rest is a simple vector addition. It will be better if you take a component wise. It is better. So I take it here as x component. I'm going to take it here as a y components. So for my x components, we have a k incident. Here is a k incident sine theta plus k reflected sine theta, or k final, same thing. Reflected one here is a k final ones. And what is my I? I here is the incident intensity a cos theta sine theta by c, and for reflected one, it is the I reflected a cos theta sine theta by c. Common factors are there, and I can say here intensity. Incident intensity is I, and reflected intensity is IR. So a sine theta cos theta by c. This is my x component of the force. But we have y component is also there, and who is responsible for the y components? Just 1 minute. Here is. So what is my y component here? Y component, I can say that. So y component we have, this is a cos, and this is cos. So minus. Okay, cos here is going to minus. So it is my kf cos theta minus k initial cos theta. So what is my k final here is? K final is my Ri. Just you have to substitute the value, that's it. Okay. So intensity of the reflected part A cos theta divided by C into cos theta. And what is my incident value of K? I incident A cos theta by C, okay? Into cos theta. तो यहाँ पे आ जाएगा, ठीक है? So it's a IR, RI minus I A cos square theta divided by C. Minus sign we can take out here common. I by C, 1 minus R A cos square theta. That is here my y components. So this y component, which is perpendicular part, just come from the pressures. So this you can get here from the pressure also. Okay, you can get it here from the pressure also. Sevita, okay. I hope you are understanding this point here. So let me take it here one sign again. So I'm feeling that. So what is a force? Force here is a change in my K. So this is my force here, okay? So F represent here change of K. It's a change of K, right? So change of K. So we have to write change of case. So it is not a vector addition, it's a vector subtractions. So it's a vector subtraction. So here is the 1 minus sign. Do a little bit here. What we are writing here is this force, this plus this is equal to kf. So my force is nothing but k final minus k initial is there. Na? So we have to subtract here this component also. So when you are subtracting here the components, so this factor will become plus, and this factor will become here plus. So I hope you understand the idea behind this process. Okay, so no one has a doubt here. So think from the flow point of view. The radiation is going to be carrying the flow of momentums, and just like a water stays the flow in the momentums. So if you want to change that momentum flow, you need a force. That's it. Yes, Sunal.
Sir, perpendicular component of force is given due to which force, sir? Like parallel is given.
Parallel is given.
Sir, no, perpendicular is given due to the pressure, no, sir?
Yes, it's going to be given. You can think.
Sir, then how is parallel component created?
There is going to be a pressure here. You can understand here this way. Pressure is a one part of the force. Okay, it is not going to be the complete pictures. Even though this chapter we have a pressure only in our syllabus. Okay, so I had discussed here this is a more general concept than pressure is a momentum concept here, momentum transfer. So momentum transfer is a more general pressure. So pressure does not take a complete pictures. So yesterday I just taken here as a pressure concept here, and today we discuss about this momentum. Momentum is responsible for the pressure also.
But
so if you go here,
we are defining momentum based on pressure only.
ये तो तुमने सही कहा. You are right. We are defining here the pressure based on this concept here.
Sir, then how will the horizontal component come?
Just understand here. There are two types of effect is there. In the case, one is the effect on the radiation. We are seeing here the effect on the plate. Effect on the plate. Okay, so effect on the plate we are seeing here. So on the plate, we can think this way. So there is one is the atmospheric pressures. You can relate here the atmospheric pressures, and this atmospheric pressure is where one is a pressure feel by us. So pressure feel by us is caused by the atmospheric pressures. The same way here, this question is about the plate, not about the radiations. So in the case of radiations, your pressure and the momentum transfers, they are going to be it's going to be in the same directions. Pressure and momentum transfers are exactly related quantity. Pressure is a scalar part of the momentum transfers. But here we talking about the external effect. So external effect on the plate, you have to go beyond the structure. Na? So what is happening inside the radiations that we have seen? Now, in this question, we are not seeing what is happening inside the radiation. We are seeing what is the effect of radiation on the plate. Okay. Now,
Okay,
on
sir.
the plate, I can find out the effect of a force through the impulse parameters, not from the pressure parameters. Why not from the pressure parameters? Because pressure is a scalar quantity. So radiation pressures is a scalar quantity. So it will give me the effect in only in the perpendicular directions. So pressure always give a force in the perpendicular directions. So about the parallel directions, pressure say nothing. Okay. About the parallel direction, pressure say here nothing. So for parallel direction, I need to take another thing, another approach, and this another approach here is the impulse approach. We can think from the impulse point of view. And I'm thinking from the impulse transferred on the body. Okay, impulse transfer on the body. So here we apply that action reaction ideas. If you are changing the impulse of the radiations, if you are changing the momentum of the radiations, so radiation also changing your momentum also. If you are changing the force, if you are applying the force on the radiations, so radiation also apply the force on you.
Sir, how is
So
the impulse
in this-
transfer, sir? Even that is because of the radiation pressure, no?
Because of the radiation pressures, it's going to be understand here this way. All are coming from the energy. Energy here is transferring, and energy transfer, along with the energy transfer, you have momentum transfer, and along with that, you have pressure transfer. Pressure is there. So both are related to your energy transfer concept here. Okay,
Yes.
we derive it. I agree. I derive it from this pressure. I derive here the impulse. But this derivation, I told you that these derivations are a very rough derivation we have in our syllabus. They are not from the first principles. They're not at all from the first principles.
Okay, sir.
Again, yes, they are analogy relations.
Sir, if they ask the magnitude, sir, then directly we can take root of ki square plus k square plus 2ki kf like that, sir. Cos of 180 minus 2.
If they're asking here the magnitude, so you can take here, you can subtract this kf and k initials, and there's a vector subtraction, the formula for the vector subtraction, you can apply that.
Okay.
Okay, you can
Sir,
apply
in
here
this,
that.
sir, in this diagram, you took ki like continuation of the incident, no, sir. So in this, we are getting direction below, no, sir, like east of.
Incident rays and the reflected rays. For incident and the reflected ones, we have taken this two part, incident one and the reflected one. So incident is transferring the momentum. Incident tried to transfer the momentum in this direction, but it was stopped by the plate. And my reflected one is also transferring here the momentums. So it was given by the plate. So I can say that here the plate stopped the momentum. In this direction, the plate has given the momentums. Okay.
Okay, sir. Understood.
So change in the momentums give me the force by the plate.
Okay, sir. Understood.
Understand? Right, but I hope you're understanding here this point is. Sorry, good. So quickly here, try to give me that one more situations. There are many problems are there. So like that, they can add the spring effect, they can add here the pulley effect, they can add here any mechanical effect, and they can put here the radiation pressures. So you can approach in the same way. Suppose I say there is a plate, and this plate is going to be attached here. Imagine it's going to future spacecraft, or in our future somehow, if we are technology is going to be advanced. So imagine this is going to be a plate, and this side is going to be our spring systems. So on this one, I'm going to be have a radiations are coming. So radiations are going to be coming on this plate with the intensity of my eye. Okay. So can you tell me here the compression in the spring? Spring constant here is my K, area of the plate is A, that's our spring constants. Find the compression in the plate spring. Find the compression in a spring. If the plate is metallic. If the plate here is metallic. So metallic means the reflection coefficient is 1. Metals are very good reflectors. So they mostly transfer 100% of the energy. So you're going to be have 100% reflection is theirs. Yes or not?
Sir, zero compression.
Zero compression. Why zero compression, beta?
Sir, when incident and reflected will be same, then no force will be acting.
Incident and reflected are the same. You're right, but directions are opposite here. So think here this way.
Sir, we'll get
Incident
two
is
times.
going to be sending the momentum in this directions, right? There is a momentum coming from the side, and it is tried to be crossed through the plate toward the right side. Now I can have a plate is theirs, and I know that reflection happens. So after reflection, radiations are going to be on the left side. So momentum of the reflected radiation is going to be crossed in my this directions. Okay. And what is the value of K? The value of K here is our power divided by C. Power is IA, cos angle here is 0 divided by C. On this situation, I'm going to be have both are same in magnitude, but direction is opposite. And this being a vector quantity, okay, this being a vector quantity is yours. You can see it in this case. So there is a force exerted by the plate on the radiations. So force on the radiation, I can say is it's a K final minus K initials. So on the plate, there is a force exerted by the radiation also. If my radiation is changing the momentum, so there is a change in the momentum of radiations. So there is a force from the radiation also. So my radiation force is theirs on the right side. And one is my spring force is theirs. So radiation force is toward the right side. So spring force is toward my left side. So in equilibrium situations, we can say both are balanced. Okay. Right? It's going to be a balance, yes. So what about my force on the radiations? Force on radiation here is change in your K value. And both are equal and opposite. So I can say it's a twice K only. So twice I by CA. That is the force on radiations. And on the plate, you have force by radiations. So force by radiation on the plate is the same as the force on the radiation by the plate. Okay, equal and opposite is this. So just you can balance it here. So you can say this 2I by CA is equals to KX. Correct? चलिए आइए सुना बेटा.
Sir, if we take at an angle, sir, then there will be no effect due to parallel components.
If we consider here at an angles, so next part you can try here with angles. So if I just tilt it, then what is the answer here? So slightly, if you're going to be tilt, then what happened? So try the same problems with the tilt also. Imagine that the light ray incident at an angle of theta had to reflect back at an angle of theta. So it is coming here incident angle I, and they reflect here back with the incident angle I. It's a metal with a reflection coefficient here as 1. Now, how much is the force exerted here? Now, one thing is here, in this case, you can understand that momentum transferred, if we consider here the momentum is going to be transferred. So in this case, you can consider this way. Let me draw it here quickly. So momentum transferred by the incident rays. Momentum transferred by the incident rays. It's going to be transferred in this directions. That's my incident one. And what is the final one? The final one is going to be here. This direction is going to the final one. Here is our final, right? So you're coming at an angle and you're going at an angle. So change of that is going to be my force. So because they are equal, I's are same. So momentum carried by the incident wave and the momentum carried by the reflected wave, both are equal. Same intensity. If R is same, your intensities are same. So I can say magnitude wise, both are going to be equal. So if they are going to be equal here, so what is the direction of force experienced by radiations? So this is going to represent here my change of K. So change of K is nothing but a force on the radiations. They have equal value. So by symmetry, I can say this is going to be horizontal. Okay. I hope you understand here. This angle is theta. This angle is going to be a theta. So clearly we can say that sine components are cancelling out. So we can say that force, which is a delta K, force on radiations. Force on radiation. So it is caused by my change of K. And the change of K, which is responsible here, is cos or sine. Sine is equal, so it will cancel out. Okay. Cos is only going to be add up here. You're taking not addition, you're taking here the subtraction. So in the subtractions, who is going to be cancelled out? Sine component is going to be cancelled out because they are equal components. So cos is going to be add up. If you want to write, you can write in the x or y component wise also. So you can write exactly also. Let me write here K final. So K final is what? K cos theta minus I. And obviously directly visible here, but if you have a problems with the directions, you can write it here as exactly mathematically. So what is my K final and K initials? K final minus K initials. What is K final, Rita? So K final has an X component, and that is my minus K cos theta I components. Y component is minus K sin theta J. That's my K finals. Same way you can write here the K initials. So K initial we have is the K cos theta I minus K sin theta J. Right? So this sine component is cancelling out and cos component is adding up. So you're going to have minus 2K cos theta I. If you write here only mod, it comes out to be a 2K cos theta. K is how much, beta? K is a power. K here is our power divided by C. And power is I dot A. Okay, so K is a power divided by C, and power is nothing but I dot A. So I can say in the situations, the force on the radiation is a 2I by C A cos square theta. The force on the radiation is this, and by action-reaction principle, I can say if radiation experiences the force, so same force is exerted on the plate. We can draw the free body diagram for the plate. So two forces are there. One force here is Kx. So radiation force is going to be in my opposite directions. So both should be balanced for equilibrium conditions. So compression, you can tell me how much is the compression we have. Kx is equals to our radiation force. Now this is a radiation force on the plate, and radiation force on the plate is opposite to the radiation force on the radiations. Okay. So I hope getting this point clear. Yes, Akash.
Say in the third quadrant, K initial is closer, where you have
K initial.
should come in the third quadrant. Then
So if you have a doubt, you can draw the diagram here once again. Beta. Last question I draw now, same way you can draw it here. If you have a still confusions, I thought you can understand the diagrams this way. Incident rays are coming this way, and where is my reflected rays? Reflected rays are going in this way. So incident rays give me here the initial value of the K. Reflected waves gives me here the final value of the K. Okay?
yes, I got it.
Incident rays carry the momentum in this directions, and reflected rays carry the momentum in this directions.
Okay, sir.
Okay, I hope you understand this point here. So both of the idea, I hope you understand here. One is our pressure, and second one here is our impulse. Both are important here. Sometimes pressure is easy, sometimes impulse is correct. So impulse is never easy. Pressure is always going to be easy, but sometimes there is a mistake in the pressure concept here. So impulse is always correct. So that's why I discuss here the impulse method also. Okay. So both methods are going to be important here. So I hope you understand both these methods. Okay. So try to do some little practice. It gets very easy. It's not a tough one. Quite easy topic is this. So related to this momentum and the impulse, we can now come to our photon once again. Radiation and photon, what is the link between them? Yeah, radiation is a classical concept here. Okay. So radiation means electromagnetic wave. Photon means quantized electromagnetic waves. That is a difference between the radiations and the photons. Okay. So if I quantize the radiations, that become a photons. So it's simply a quantized version of the radiation. Here is a photon. That's it. Photon is nothing but a quantized radiations. So here it doesn't mean that photon is not a radiations. Photon is an electromagnetic wave. Okay, it is an electromagnetic wave, but it is a quantized. But what do you mean by quantized here? So meaning of the quantized, I told you many times that quantized means it will take energy in a packet. It will give energy in a packet. So energy exchange is happening in the packet. That is the meaning of quantized radiations. It doesn't mean photon itself is a packet. Photon is not a packet. Don't think that photon is a packet. So it's a quantized radiations. So any energy exchange happens, that is going to be happen in the packet. Now, if I ask you one simple questions, if I ask you here one simple questions, and that question is related to your little misconceptions. Do the photon has a size? Is photon has a size? Photon has a size. Now, if you are going to be think it from the mechanics point of view, or just little bit of confusion is going to be generated by the chemistry. So you think that answer is yes, photon has a size because photon is a particle. So answer here is no, photon has a no size. It doesn't occupy volumes. It is a quantized energy. So when I say photons, so photon does not mean it is a package. It doesn't have a volumes. So photon has no volumes because photon is not a matter. Okay, it is not a matter. It's the radiations. It is electric and magnetic field. Photon is electric and magnetic field. So what is why it is called particles? It's going to be simply according to quantum theory, energy exchange is going to be happen in the particles. Okay, it doesn't have any volumes like electrons or protons. It doesn't have a volumes like our atoms, right? So there is no volumes. So it's a question of how to imagine the photons. So it's going to be the whole of the problem is going to be created if you try to think to imagine as a photons. So you need to imagine the photon as a wave only. Photon is a wave only. So if you want to imagine the photon, don't imagine the photon as a bullet. That's the wrong picture. Photon is not a bullet. So this imagination is going to create here the confusions. So in picture, if you want to take here the photon picture, so it is going to be a wave, right? It is a wave. Photon is a wave. So you're done. Now, if it is a photon is a wave, so what is quantized? What is quantized here? So energy go, and this energy is not continuously going. It is going to be transferred in a packets. That's it. Energy transfer is happen in a packets. So there's not a continuous transfer of energy. There is a discrete transfer of energy. That is the meaning of quantized. Okay. It is a quantized radiation, but it is a radiations. So I hope you understand the meaning of photon here. So photon has energy exchange in a packets. This packet is HF. Size of the packet here is HF. That is something important here. I hope you understand here this diagram of the photons. A lot of confusion happens with the picture of the photons. So if you want to take the picture of the photons, so don't treat it like a particle, don't treat it like a bullets. So photon is a wave and it has a no volume. Okay? No volume is there in the photons. Okay. So because it's a wave, if I ask you the photon has a mass, photon has a mass. So photon has a mass. The answer here is no. There is no mass is there. Okay. So it has a no rest mass. Now what is the meaning of the rest mass here is? Now this concept of the rest mass is what you understand as a mass. So mass of your paper, pen, stones. So that type of mass is not there in the photons. Okay? So whatever the feeling you have about the mass, that feeling is not present in the photons. Okay. So there is another meaning of the mass is theirs. That's called here as a dynamic mass is theirs. That I will discuss in the next week when we discuss about the nuclear physics. But whatever your sense of meaning of the mass is there, whatever your feeling of the mass is there, this type of mass is not present in the photons. It has no rest mass. The next question come here is that photon has a momentum. The photon has a momentum. So meaning here is that it's going to has a momentum or not momentum. So that is not at all important here. What is important is that can it transfer the momentums? Yes. It has a momentum or it don't have a momentum. That is going to be a totally different stories. It go beyond our syllabus. So question could be changed here as can photon transfer momentum? Yes. Photon transfer momentum. This is important here. It can transfer here the momentums. Sevda? what is E here? E is not the energy of the photon. E is the energy transferred by the photons. Remember that. E is not the energy of photons. It is the energy transferred by the photon or transferred by the radiations. Okay. So this transfer is named as a photon basically. So don't try to get confused here. Is when energy is transferred. So during the transfer, it is called as a photon. So size of the energy transfers. That size of the energy transfer is called here as a photons. So that's small difference you should have. It's almost similar to the heat concept of heat in thermodynamics you have done. Heat is energy, yes, but heat is only between the two bodies. When the energy go from one body into the another body, so at the boundary it is called as a heat. Okay, so when it is in the first body, it is not called as heat. In the first body, it is a kinetic energy. In second body, it is a kinetic energy. When energy is transferred from kinetic to kinetic, in between it is called as a heat. So same way is theirs. So energy is theirs. Okay, energy when it is transferred, then it is called as a photons. Energy transferred is called here as a photons. So packets of the energy transfer is called as a photons. So because there is a relation, I just prove it here. Impulse and momentums. So there is a momentum transfer is there. So impulse transfer is there, and this impulse transfer here is a momentum transfer is there. So that momentum transfer I can say here E by C. Okay, momentum transfers.
Sir, in an atom,
Yes,
when electron makes transition from one state to another state, even that energy released also is a photon, sir.
the question is that atom make a jump. Okay, so where the energy will go?
The electron released kinetic energy.
You can think of atom just like our simple spring block system and wire. So this spring block system, it will lose the energy, and this loose energy will go to the wires. Yes, wire begin to oscillate.
Yes, sir.
Right. So atom is behaving like a spring block system, and this atom is transferring the energy to something, and that something is nothing but my radiation field. You can say electric and magnetic field. So it transfer the energy to the electric and magnetic field. So in this process, when it is transferring the energy, that during the transfer it is called photon. After that, it is a radiation. Okay.
Yes, sir.
Okay. So
Yes, sir.
energy exchange between the atom and the radiations happen in a packets. So that packet is called photons. I hope you understand here the difference.
Yes, sir.
Just as you have a hot body is there, cold body is there. So there is a hot body means high kinetic energy of the molecules. Cold body means low kinetic energy of the molecules. So heat means what? Kinetic energy of the hot body go to the kinetic energy of the cold body. That is the meaning of heat, right? And in between, when the kinetic energy is going from hot body to the cold body, the same kinetic energy we call as a heat. Same way, energy is coming from atom into the electromagnetic field. But this energy is not coming continuously, it is coming in a small packets. So that small packet we named as a photon. Okay, so before the photon, it is atom energy. After the photon, it is electromagnetic energy. In between, what happened? We don't know. In between, what happened? I don't know. Okay. For example, if I ask you, there is a current, and current is going to be rotate your phone for your fan. So current energy convert into my kinetic energy of the fan. So in between, what happened to the energy? So it's a meaningless question, na? The energy of the current going into the energy of the fan. In between, what is the form of the energy? It's a meaningless question, nonsense questions. Current energy going into the fan energy, that's it. That there is a transfer, there's a process of transfer. So in between, what is the name of the energy? It's a nonsense questions. Okay. But in between the transfers, it's a nonsense question, but we have given it a name, photon. So photon is not a new type of energy. It is just a name for the process. Because in our Newton idea say that this atom energy will go into the electromagnetic energy, and this transfer is a continuous. Einstein say no, it is not continuous, it is happening in the packets. So that size of the packet is just a name of photons, nothing else. It's not a new type of body, it is not a new type of energy. So photon is the name of quantization process. I hope you understand, yes, the meaning of photons. Okay? So photon is a quantized process of energy transfers. So in this transfer process, momentum transfer, yes. Energy transfer, yes. Energy and momentums are related, just I prove it here. See that radiations. We have proved here that momentum transfer. This is a impulse transfer is there, energy by C. That is our energy by C is that impulse. So impulse transfer here. So during the transfer, in between the transfer, we call it as a photon. So that become photon momentums. Right? So photon has a momentum. It's E by C. Correct. Correct? And I can also write energy of the photon is hf by C. So we can write here this as a h by lambda also. So momentum of the photon is h by lambda. It's related to lambda. Lambda is not responsible for the momentums. Wavelength is not causing the momentums. There is a relation between the wavelength and the momentums. Who is the cause for the momentum? Energy exchange is a cause of momentums. There is an energy exchange, and energy exchange between energy exchanges my momentum transfer, impulse transfers. So energy is responsible for the momentum. I hope you're not getting confused here, right? So yes, Akash. Repeat again, I'm not getting your voice, Beta Akash.
Sir, my internet connection was
Internet, okay. So what I'm telling you here, it's just a little misconceptions are there. A lot of misconceptions are there regarding the photons. So I'm trying to remove this misconception regarding the photon here. So simple idea is that what is a photon? Photon here means quantized radiations. If I ask you that photon has a size, so answer is no. It doesn't have any volume. It has no volumes. So meaning is simple, Vida. Photon means when your atom exchange the energy with the electromagnetic field. So we have electric field, we have magnetic field. This is called radiation. Or in between the atom and the electromagnetic field, energy is exchanged. So this exchange of energy, the packet of energy is called here as the photons. Okay?
the third point, sir.
Then is a photon has a mass. So Rex mass is not there in normal sense. Next is a photon has a momentums. So because it's a transfers, photon means during the transfers. So during the transfer, momentum is there. So there is a momentum transfer. So that momentum transferred between the atom and the energy, electromagnetic waves. So momentum transfer between the atom and the electromagnetic waves, that is, you can call it as a photon momentum, E by C. That's related to your wavelength h by lambda. Correct, Beta? I hope you understand the point here. Now, next question here is, which is a little more confusing here is, in fact, it is going to be more confusing here is, what is the meaning of intensity then? Intensity, meaning of intensity. So here it's very easy. The meaning of intensity is the same as the meaning you learn from the intensity in our wave chapter. So photon does not change the meaning of intensity. It is not at all going to change here the meaning of intensity. It's the same. So meaning of the intensity is the same. So what is the meaning of intensity? Meaning of intensity means power transferred per unit area. When my spring block is oscillating, it is transferring the energy. So power transfer per unit area, that is my intensity. But here is, what is my power transfer? So it does not change any meaning of the intensity, not at all. So it is power transfer per unit cross-section area. So what is happening here is that the photon idea simply say that this transfer of power is happen in a small packets. Okay? So it is going to be transferred in a very small packets. So this continuously, if I say that n is a number of packets transfer per second. If I call this n represent the number of packet transferred here per second. So each packet will the energy of packet. The energy of packet is just that is the primary energy. So what is the total energy transfer? Total energy. So we have n packets. Energy of packet is E. So that is my total energy transfer. Now if I go here for second, for seconds, the total energy transfer per second. What is the total energy transfer per second? Transfer per second. How much is that? So it is the number of transfer per second energy of one photon. So it is n and another energy of one photon is HF. And total energy is nothing but power. So is it change any meaning? Is it going to change any meaning of intensity power? Not at all. So there is no change in the meaning of power and the meaning of intensity. Only it is simply that because energy is not coming here continuously. So energy is coming in small packets. So power here. It's the number of packets changing. Right. So power here is simply how number of packets changing. So power is simply directly linked with the packet size of the packet and number of packets. That's it. That is measurement power. So everything else is going to be made the same. Okay. Everything else is going to be made the same. So quantum physics has no impact on the definition of power. Quantum idea has no impact on the definition of intensity at all. It is the same. So what is the quantum doing is the quantum saying simply is the way. So you think that this is a light bulb and say that the light is coming out continuously from the bulb. It is continuously shaking the wires. So bulb is something who is continuously disturbing the space. So quantum theory say that it is not continuously disturbing the space. It is disturbing in the packets. That's it. Yeah, it's not a continuously disturbance. Even though it is continuously disturbance, but energy is not continuously coming. So energy is coming in a small packets. So as I told you, Bohr says, if energy come in a packets, then everything comes in a packets. So yes, at the atomic levels, everything comes in a packets. But for our daily life, it appear continue. So at the atomic levels, you feel that energy is coming here as a small packets, but we feel it is coming here continuously because number is very high. Number here is very high. So this number go high because h is very small. Planck constant is very small. So because of this small value of the Planck constant, I'm not able to see a discontinuity. I'm going to see a continuity. So what we learn from the Newtons, what we have learned from the classicals idea, this is absolutely applicable for us. There's nothing, no mistake is there in that. It is continue the same way. The idea we have learned is going to continue the same way. Only thing is that is happening in a small packets. That is the quantum meaning. So I hope you understand this point here. If Okay, for example, if I say that this is a light bulb is theirs and it has 100-watt power is theirs, and you are going to be standing there at some distance of, let's say, 10 meters away. You are standing at 10 meters away, and your eyes, this is the size of your eyes, eye is this, and you are watching the bulb. From 10 meters away, you are watching here this bulb. And when you are watching, your diameter or radius, the radius of your eye is how much? Let's say 10 millimeters. If 5 millimeter, so radius of your eyes is 5 millimeter is your radius of eyes. So question here is that how many photons enter your eyes? How many photons enter in the eyes per second? How many photons enter in the eyes per second? If the frequency here or wavelengths, we can give you a wavelength here. Let's say the wavelength here is at 500 nanometers. If the wavelength of light is of 500 nanometers. So how many photons enter in the eyes per second? I can also ask here that radiation pressure on the eyes. What is the radiation pressure on the eye? So quite easy and simple one is theirs. So first one we can just find out here from the simple way that how much energy is going to be transferred through the eye. What is the power through the eyes? What is the power through the eyes? So power through the eyes depends upon the intensity. When the light is spreading, so this 100-watt power of the bulb, it will spread in every direction. So it will spread with the 10 meters. What is the size of the wavefront? So the 100 meters, sorry, so 100 watt, this 100 watt try to spread in everywhere. So how much intensity it will give? So that's my starting power of the bulb is this. And on the eyes, I can find out the intensity is power divided by our radius. So it is spreading. The power coming from the light bulb is not going to be go in a one particular direction. From the bulb, it is spread in every direction. So wavefront increase its area. So cross-section area when this light is crossing here. So as my light is crossing, so area of cross-section becomes my surface area of the spheres. 4 pi r squares. That's my intensity on the eyes. The next step is that when you are going to see your eyes, so on the eyes, we have radiations are coming, okay, as an eye, and this is my area of cross section is this. So how much power is passing through the eye? So intensity on the eye into the area of the eye, okay, and intensity on the eye is coming from the power of the bulb. So bulb has spreading the power in every directions. So at r distance, intensity left is power by total area of the wavefronts. So I can say that the power fall on the eyes. How much is that, Rita? Intensity on the eye into area of the eye. Area of the eye is nothing but a pi r squares. And what is the intensity on the eye? It's a power by 4 pi. Oh, so here we have two radius. So I'm changing the symbol for the radius. This is capital R. Let me take it here. So that is going to be here power fall on the eyes. So pi is going to be cancelled out here. So we're getting here P naught 1 by 4 r square by capital R square. That is the power fall on the eyes. Correct. That is the power fall here on the eyes. Now if I say this is a power falls, so this power is not coming here continuously. This power is coming in a small packets. So if you want to find out here the number of photons, okay, number of photons crossing per second. So what does that mean here? Number of photons. So it is a simply you can relate here is if we have n number of photons are there, each photon has energy hf. So n photon is going to be have energy n times hf, and this is power per second. Just give me the powers. So clearly here n is equal to my hf. The number you want here, so it's a power by hf. So power is a big concept here and hf is a small concept here. Okay? So total power is made up of small powers. Okay? Small packets of powers. That's it. So power we have done it is P naught 1 by 4 r square by capital R square divided by hc by lambda. You can put the value and you can get the answers. Take it up. I hope you understand here this procedures. Procedure is very simple one. It's a just basic one is yes, nothing special here. Okay. So criteria is that from the classical's idea, from the old idea, you have to find out the intensity and pressures. So there is no effect of quantum on the definition of intensity and the pressures. Okay, no effect. What is the effect here is? Quantum simply say that the energy exchange is not happening continuously. It's just happening in a small packet. That's it. Okay. Actually, I hope you understand this point here. Okay, you can put the value, you'll get the numbers. So anyone have a doubt here in this quantum? Yes, Shiva.
Sir, here pressure on the eye is the radiation pressure, sir.
Radiation pressure on the eyes I'm asking here. This is power.
Okay.
The power is intensity into area is a power.
Yes, sir.
So radiation pressure, what is my radiation pressures? Radiation pressure, we already has done it.
Intensity.
You know the formula here. So radiation pressure, just you can say here in this case, it is I by C. It's no reflections. I does not reflect anything. No reflection. All the light will be absorbed. So it's a R is 0 for the eyes. So pressure is simply I can write I by C. Okay, I by C. Intensity we have calculated here, so we can put the value of intensity. And this has nothing to do with your photon concept here. Okay, nothing to do with the photon concept here. Intensity, we already know it is P naught by 4 pi r square divided by C. So whatever may be the size of photon does not matter. The pressure you feel has nothing to do with that photons. What is important for the pressures? It is important that how much power is sent by the light bulbs. So in my daily life, so what is the size of the photon does not matter. How much power is sent by the bulb, that is only going to be matters. So that's why what happened at the atomic levels, it's have a negligible role in our life. So when it has a negligible role in our life, so whatever we learn from the Newton's perspective, this is going to be play a very important role in our daily life. But when you try to understand the nature at a deeper level, then Newton failed. Then Newton is going to be failed. You have to modify the concept. But for as long as your daily life is concerned, Newton is perfect. No problem. Sivida, I hope you understand the point, yes? Okay, good. So I hope I try my best to avoid the misconception in this chapters. It is unavoidable to avoid his misconception in this chapter because a lot of misconceptions are there in this chapters. But I hope so. You are not getting the trap in the misconceptions. You are understanding this concept of the quantums. If you understand here, it's well and good. But as I told you, our syllabus is a quantum, but our approach is Newton only. So remaining we will do here next class. Okay. Next class we discuss about our photoelectric effects. Now, if you have any doubt in any question, you can ask me that doubt. Okay. And remaining you can try the problems. Yes, Sunat Garu.
Sir, I have doubt in X-ray concept, sir. Sir,
Tell me what is the doubt here?
Sir, how that X-ray is created, sir, when some other electron from outside is coming and hitting the electron in the shell, then that excitation energy is created as X-ray, no, sir?
Excitation energy created as X-ray, right?
Sir, then that excitation energy, like electron in the lower shell only is eliminated, or any electron, any shell that can be eliminated, sir? In HCM, all the example.
Any could be eliminated here. I told in the class, beta, vacancy can be created in the K shell, vacancy can be created in the L shell, M shells. In fact, creating the K shell vacancy is the most tough.
Yes, sir.
Okay, it is most tough. L is easy, M is easy. So higher valency is easy.
Yes, sir.
So why you're getting that confusion? I don't understand. What is your doubt? Repeat again.
Sir, in HCM, all the examples he said that electron is eliminated from the K shell only, sir. In all the examples, that's why.
So no, it is not necessary that by chance.
Okay,
You
sir.
can
Sir,
have a L also.
if the vacancy is filled from a more higher shell, then more frequency of the X-ray is created.
Yes, more energy, more frequency.
Okay,
You're right.
Okay. Yes, sir.
I told you that there is a K alpha line. Alpha line
Yes, sir.
is the shortest energy, minimum possible energy, because you jump from 2 to 1, n equal to 2, n equal to 1. Then we have
Yes,
K
sir.
beta line is possible. 3 to 1 jump is there. Can K gamma possible? 4 to 1 jump is possible. So anyone can fill the vacancy, but it's a question of probability. So probability is that K vacancy is a maximum filled by the L vacancy, L electrons.
Okay.
So
sir.
based on that, we have K alpha, K beta lines. So question they can ask you for anyone, it will be mentioned in the questions. Very
Okay.
easy questions are there in the X-ray, not a tough questions. Very easy questions are there. Achha, yes, Shiva. Hello. Hello.
Sir,
Bolo Shiva.
sir, can you send DPP on this power intensity impulse?
I sent na 1 DPP. No.
No, sir, you didn't get.
Oh, so sorry. I'll send you. Uh, just I will send you. I thought I sent. Sorry, sorry.
Okay.
I will send you in after the class. I will send you. So you try from material or HC Verma or any book if you have. Try it from that side. Okay. Hello, Sai. Number beta. Five two nine eight seven. Short series of the Balmer they have given. Find the atomic number of the element which give X-rays wavelength down to 1 angstroms. Here in the questions, a lot of things are missing. The first thing, he is not mentioned any particular X-ray, K line or K line, L line. Nothing is clearly mentioned that which line he is talking about. So let's say because K is give me the maximum energy. So इसमें तो बहुत सारी possibility हो सकती है. Lot of possibilities there in the questions. They are given Balmer series, but that Balmer series for the hydrogen. Okay, we can also take it Balmer. Okay. So these are a lot of possibilities are there. Any transition is possible here, but this question is not very clear. From where is that question? Narana materials. The 1 angstrom here, suppose we can jump here, you can jump here, you can jump here. So many jumps are possible. You can have vacancy in the K shells. You can have vacancy in the K shells. You can have vacancy in the L shells. So many possibilities are there. Okay. And they have given short series limit of the Balmer series for the hydrogens. What is the meaning of that? Short series limit. So series limit means from infinity you are jumping back to the ground one. Balmer is there for n equal to 2. So we are making a jump up to the 2. From where? We can do it up to the 2. So from infinity, you are jumping here down to the 2, right? So this one wavelength is given to you, and this wavelength is given here 3644 angstroms, right? That is the wavelength they have given to you. Now directly you can't relate the hydrogen atoms with the other one. What is the meaning of the question? That's not clear. Maybe he say that you are using it another elements, and for the same wavelength he want 1 angstroms. Maybe that may be the meaning of the questions. If you want here same line with the 1 angstroms. So if I take it here same line with the 1 angstroms, so same line with the 1 angstroms, so I can apply this models, energy is equals to energy here is at C by lambda, so it is equals to my R at C. Z will be here Z minus screening. So vacancy here is in the L shell, right? K shell, 2 electrons are there, and we have vacancy in the L shells. But in this questions, if I think of same transitions, so jump is from the infinity and jump is from the infinity, then all the electrons are making a shielding effect, not only K shell. The question is not very clear. I will check it, what he wanted to say. There is not a clarity in the questions. So next question, you can say the K absorption edge of an unknown element. He is absorption edge. Identify the element. Identify the average wavelength of the K alpha, K beta, and K gamma lines. Absorption edge here. K absorption edge here. So K line, we have K alpha, K beta, and K gamma line is there. So if there is, this is my K alpha line, transition from n equal to 2 to 1, and the last line is taking here as a edge. The last line is going to be called here the edge line. Okay, normally that is called here as the edge lines. So I'm not clear whether he's taking here K alpha or infinity. Edge means corner. So the two corners are possible here. This is also one edge, or it is also going to be one edge. So normally this is the name is there, alpha, beta, gamma. It's the naming of the rays are there. So last one we don't have any name, so it is called generally as a limit or edge line. So normally we use the word here edge for this line. But for this transitions, it is difficult to find out because screening is not clear. All the electrons are going to be screened. So this line is difficult to find out. So maybe he given the answers to the K alpha line. So K alpha dekh lete hain, okay? Let's first try here the K alpha line. So K alpha line is 1 by lambda, that is equals to R. Z value for this transition, my one electron is there in the K, one is removed. So shielding we have for the one electrons. Shielding we have for the one electron. So we have R Z squares, and transition you can consider from 1 to 2. So let's give me here lambda lines. If we do here this lambda line, so it comes out to be this is given. R is standard value, Z you can find out. So again, so you can try this way. This is the best possible. Normally, edge lines means infinity lines. So for infinity line, you sometime in some books, nonsense books, so they give this way also. They don't take a screening, and without screening, they also give the answer. This is not correct. Okay. X-ray, the topic of the X-ray is basically to understand the screening phenomena. That is the purpose of this chapters or this topic in this chapters. So without screening, if you do it, so I don't feel it is to be a correct one. But edge means this line. I hope so. In this question, he is taking K alpha line as an edge line. If he is taking this, if he is taking here the infinity line, then he neglected the screening. It is also from the nanomaterial. So we taken here the infinity line, so he has neglected the screening. So without screening, he is doing. So screening effect is considered, and what is the screening value taken? 1. So you can't take a 1, no? That is a nonsense. So when you are taking a jump from the infinity, screening is done by L electron, M electron, all the electron will do the screening. So that is wrong. Solution is wrong. If they had taken one screening, then solution is wrong. Okay. Yes, Durga Satvik. Hello.
Hello, sir.
हाँ बोलो दुर्गा बेटा.
Sir, someone is coming in my name Telegram, sir. Sending you message.
I don't read Telegram message. Don't worry.
Okay, sir. Okay, sir. Sir, I have sent you one question. 7244.
7244. Just a minute, yes. So understand here beta one thing in this experiment. So you can also see here as recap. So basic idea in the X-ray experiment is that you have a tube. In this tube, we're going to be send the electrons from low to high energy. So this is the basic purpose of the experiment, and what these electrons are doing, they're going to be hit the heavy metals. Okay. So this is my batteries here. Now this battery provide the energy to the electrons. Correct. These electrons are going to be hit, right? And this electron only going to generate you the current here. So what he's saying, the question is, these electrons are going to be generating here the current. So in this question, he is assuming that all these electrons are going to be generate the current, but it's wrong. In actual experiments, these electrons are going to be radiated out also. So electrons are coming out of the tube also. So saying that current is conserved, it's wrong in this topic here, because yeah, in many books, what they think of there is only one battery, but these are two batteries are basically. So this is a one more battery. There's two circuits are there. So second circuit is theirs who generate the electrons. So these electrons are outside my primary circuit. Okay. So current conservation is not a guarantee for the circuit here. I hope you understand the point here. So these electrons are going to be hit, and these electrons are coming out. So
Yes,
it was something maintaining this current conservation is something is going to be a silly in this experiment, but there are some books who give the answer by assuming current conservations. Okay, so they think of as a single circuit. So it is not a single circuit. Electrons are also leaking out. So there is leakage of current also. So if we neglect that leakage, assume that all the electrons are keep on revolving, no electron is going to be comes out, then you can think about this problem here. He simply say that there is a gap between them. Here is a gap is given here. This gap is given here T. And he said that there is a current I. Current I is there. This current is going to be I is there. And the target is kept at a potential V higher than the cathode, resulting in, okay. So this is going to maintain here as a potential difference, maintain here as a V. So next he say that this current is reduced to half and the potential difference is increased to 2V. So this current reduced to half and potential has been increased to 2V. So this potential increased to 2V and this current is reduced to half. And next he said this gap is also decreased to half. So this gap has been decreased to half.
Yes, sir.
So these are small changes they have done. The gap between the positive negative that is decreased to half, current decreased to half, and potential here increased to half. So this changes in the setup has nothing to do with our X-ray phenomena. All these setup changes has nothing effect on the X-rays. So phenomena of X-rays is totally independent. The reason we have discussed for the X-rays, so this is totally independent. So all that effect you have to be analyzed from the electrostatics point of view and current chapter point of view, not from the X-ray point of view. Okay. So see the first option they have given. Cutoff wavelength will reduce to half. So cutoff wavelength we have discussed better. Cutoff wavelength comes when that electrons lose all their kinetic energy, and the kinetic energy gained by the electron is because of this potential difference. Okay, so you have